Okay? And so for buckling of columns, what we want to be able to do is the following. These are our objectives. Our objectives are, one, is to understand or to describe the behavior of axially loaded members under compression. Okay. We have spent quite a bit of time in the very first part talking about axially loaded members subject to tension. Okay. We had the N over A. Okay. And really, when we pull this, when we pull a vertical member like this, we pull it. The only thing that can happen to this is fail by yielding. But all of you know that if I take this right here, and if I apply a load to it right here, okay, what's going to happen to this if I just push down on it? It gets really unstable and just boom, it just gives out, right? So I have a video about giving out, okay, about giving out over here that I would like all of us to watch, and this is buckling behavior, okay, buckling behavior. Oh, but before we do that, let's make sure we look at the other objective too. The other objective is to calculate, and we're going to learn this term, the critical load, the critical buckling load of columns. Okay, and really, I want to emphasize to you, a column is just a structural member, right? But really, for us, a column, what is a column? What is a column? What do you think a column is? So some people, not a beam, right? But a lot of you think of it as a vertical element, right? Something holding up a building, maybe my legs, yeah. What else? You would say maybe a column would be, you think of Greek structures, yeah, Greek structures even, and you think these huge vertical members. The reality is, a column is defined by, what do you think? How do you define a column? How are you defined? You, the person, how are you defined? By who you are on the inside. So a column is defined by, when I look on the inside, I have axial compression. Okay. Doesn't matter if it's a member of a truss. It doesn't matter if it's vertical, horizontal, or sideways. Essentially, what's going on is that all my other internal loads are zero, except for my axial force that's going on is in compression. Okay. So here, column, internal loading, where only axial load exists, axial compression is present. Okay, that means the moment and the shear, they're all zero. Okay, they're all zero. Okay, and column failure or column buckling it's a tragic failure. And let's see this video on column buckling. Critical load is this axial load. Here, I'll draw a column here, an axial load on the column. So here, this is I'll call this P critical. P critical. Okay, is the load on column just before instability occurs. Okay, just before instability. And when I say instability, I mean collapse. Okay, buckling out, all kinds of phenomenon. Right? Load on column just before instability occurs. And you're going to see terms like, and this actually in the world of structural stability, this is called a bifurcation point. Bifurcation point. It's that borderline between stable and unstable. Okay? It's like, and the analogy a lot of people use is like a perfectly round hill and a ball right here. Okay? And you know, if you go just to one side of the ball, you go just to one side, that ball's going to become unstable and fall off. Or you go just to the other side, it's going to fall off. Okay? But right on top, right there, it's stable. It's this bifurcation point. And for us right here, if our load is less than our load applied, our P applied, if our P applied is less than the P critical, then we're stable. We have stable equilibrium. And if our P applied is greater than P critical, then we have unstable. We have an unstable condition. Okay, instability. Right? That is essentially, it's a boundary for us in terms of loading here for a column or a compression load. Okay, this is a compressive load. Okay, so you're probably asking now, how do we determine, or how's it? We already knew by intuition, by looking at this intuitively, we know that it's a function of some of the properties of this cross section. Already, we talked about stability and the moment of inertia. What other properties do you think influence the critical load? Not geometric. Material properties, like what? What material properties do you think influence this buckling? The modulus of elasticity, absolutely. The stiffness. Okay? So here, we're going to have, we have this idea right now. Oops. We have this idea that this precritical is a function, it's some sort of function of geometry. Okay, so geometry. So we already talked about the moment of inertia I. Okay, I, and here I'm going to write Ix and Iy. Okay, and then we have material. And here we said the stiffness or the modulus of elasticity that plays a role. And let's see. And whoa.
Temperature play a part because, like, as temperature changes, the material fluctuates.
Absolutely. As temperature increases, modulus of elasticity decreases, and in metals, and so obviously the critical load will decrease too. It's easier to buckle when it's hot. Okay, just like a marathon runner. It gets too hot. Thank you. Okay. Yes. But so here, material, and look at what about this? Okay. Listen, I'm trying to buckle. I'm trying to buckle this right here. Oh man, I'm strong, right? I'm trying to buckle that right here. What's up, right? Right? You can't buckle, you can't buckle me, right? Then all of a sudden, well, I can buckle you, right? It's long, bam, buckle it, right? Then I shorten the length and I put my hands. Oh shoot. Right? What did I do? I changed the length, and what did I increased the buckling load. Yeah? I changed so now length. Dang, length. Okay, so geometry is I. Let's also include the length. Okay, we have the length, and then what about how I hold it? How about how I hold this? What if I hold it by my little itty bitty fingers like this, like a pin support, right? Versus let me use my fist and hold it tight. Okay, that also in fact obviously you think which way will be stronger if I just use my fingers or if I use my hands? My hands, right? Like a fixed support. Okay? So boundary conditions, supports, boundary conditions. Okay, and we're going to talk about boundary conditions. This is section 3 of your chapter. This boundary conditions, Is it fixed? Is it pinned? What is it? Right? That plays a role in how much buckling capacity I have. All right, so So here, let's consider. So we call this topic L for us. Okay, let's consider. We'll call this L1 right here. Let's consider this will be a pin column. We're going to start with just by analyzing pin column. Okay, and what that means is this is my pin column. It looks like this. It's got here. I've got a I'm going to put like this roller over here like that. Okay, and another one here like this. Okay, is everyone okay with that? I just want to isolate it so this point can only move up and down. Okay, so that's one end of my column. And then I have my column that goes down like this right here. And it's pinned right here like that. Okay. It has a length L like this. Okay. It has some load P that's applied. P. Okay. And this thing also has material properties and moment of inertia. Okay. Right now, we will not distinguish between symmetric or non-symmetric sections. We'll just say that it has one symmetric cross section. Okay. So we're going to assume symmetric for now. So E, I, L, all those factors right here. And when this thing buckles, okay, when this buckles right here, when I buckle this right here, what shape does it take? Like some curved shape, like a display shape, like as if I had the beam here like this and I applied the load like this. Yeah, right? It looks like that. Okay. Okay. So here we have right here the display shape might look something like this. Okay. So here I'll call this. Let me call that. Let's see. What does your book use? I normally use Y. Let's see. Did your book use V? Let's see here. I'm gonna try to be consistent. Yeah, they use V. So let's say this is this distance V for displacement. Okay. All right. And how do I relate? Oh man. Okay. So normally right here, how would I relate this to? Let's say, what was that relationship between displacement and moment that we use so much? The relationship between displacement and moment that we used to calculate deflections. What was that? Does anyone remember what that basic relationship was? That way I don't have to derive it. The relationship between displacement and moment. Yes, double integration method, absolutely. Moment is the second derivative of something. Of v, yes. Okay, a moment, or we had d squared v over dx squared is equal to m over ei. Yes, very good. And I can't remember if we had a negative sign, but well, it depends. You can use a negative sign, not use a negative sign. Not to bother. Okay, it's no big deal either way. Okay, let me think here. Let's use a negative sign because it's going to depend on how I define my coordinate system. And so here, yes. Yes. Oh, was there no negative sign yesterday? Okay, we'll leave it without a negative sign then. Okay, without a negative sign, and here we'll say that plus v goes in terms of our coordinate system. This is my plus v direction right here, and this is my going down. Oh, I kind of messed. Sorry about that. My plus x is, doing really bad things on my notes. Okay, right there. Okay, and so here I have this relationship between curvature and moment. which is a well, it's not a differential equation yet to you, but to find this moment, let's say at some point right here, let's say I make a cut. So here I make a cut right here. Let me draw a free body of this cut right here. So, and I'm going to draw a free body of the deformed shape. So it looks like this right here. And I have, by equilibrium, I know that this is P right here. There's some P, applied P. Internally, I have, let's see, I make a cut. I have a moment, M, a normal force, N, and a cut left side shear going like this. Okay, I have my MVN, my internal loading there. The distance here in my buckled shape, this is a distance V. Right there. Right there is that distance V. And for me, if I want to calculate the moment, so now using this free body, calculate M right here. I would take moments about this point right here. So some moments equal to 0 right here. I would have M minus P times V equals 0. Yes? Okay? All right. And in, in this case, okay, for the derivation, let's say that V right here this is a negative displacement. The way that we drew it, we drew a negative displacement. So this has to be, you're going to have to forgive me here. I'm going to say that has to be less than 0. Don't worry about it. But this M, well, that means that this becomes M plus P times V equal to 0, which means that M is equal to minus P times V. Okay? And is that okay with everybody? All right? It's because of the way we drew it here. We drew this V as a negative deformation. Maybe I should have drawn it as a positive. But that would have just, if I drew it as a positive, I would have been on the other side, and then I still would have gotten this. Does that make sense to everybody? Yeah? If I drew V as positive, if I drew this drawing with V as positive, I would have gotten this diagram right here. Okay? It would have been P. I would have had M right here. And when I did some of the moments, I would have gotten M plus P times V equals 0, and M would have been minus PV. Okay? Yeah? Just to make sure that that's clear. Okay, so now what I do here, and this is why this class requires a co-requisite for differential equations, okay, right here, also because of the double integration method, is to substitute this guy into here. Okay, and that gives me this d squared v over dx squared equals minus p over ei times v. And if I use everything that you learned in differential equations, or ODE right here, this becomes V double prime plus P over EI times V equals 0. Oh, snap! Right? This is an ordinary differential equation. A linear ordinary differential equation. Right? To what order? It's a pretty simple one. It's a second order, right? Second order, right? Okay. Does anyone know what the solution to the ODE is? A general form of the solution would be V as a function of x is equal to, you might use something like a cosine, a cosine, let me use a little c times x plus b sine of c times x right here. Okay, yeah, that looks familiar, right? And it's equal to 0, so it's a homogeneous one as well, right? Okay, there's no particular solution. So here, you have this right here. That C, that C I'm going to tell you, let me see. That C is just, that little C right here is equal to square root of P over EI. Right here. Square root of P over EI. That C is equal to square root of PI. And how do I solve for these constants? Whoa, question first? No, okay. Boundary conditions, okay? So boundary conditions, okay? So now we need some boundary conditions to solve for constants. So need BCs to solve for constants. Okay. All right. So let's see here. So let's see. Solution to ODE. Yes. Good. Right here. Let's do boundary conditions now. So let me call this just need BCs to solve for constants right here. What are some boundary conditions? Who wants to venture some? Look at the drawing up here. Bam. This drawing right here. This is what we're basing it on. Who can give me some boundary conditions? V equals 0 at x equals 0. Awesome. What? I have two constants, so I need one more boundary condition. Who's got one more? V equals 0 at x equals L. Awesome. Right? So now if I just plug in here, if I substitute now here, apply BCs right here, I get that V0 is equal to A cosine of 0 plus B sine of 0, which, you know, this is too trivial right here, equals to 0. That tells me A equals 0. Woo! Okay, there's one, right? And then here, at V of L, I have A, or this is all 0 anyway, 0 plus B sine of square root of P over EI times L equals 0. Does that seem okay? Yeah? Okay. So, whoa, okay, right here. So here's this term right here. Okay? Right here. Right there. And the only way that this part could be true is if what? If square root of P over EI times L equals what? How can this be true? This term right here. B is a constant, assuming B is non-zero. If B non-zero. If B not 0. Okay? What's the only way that this term, this bubbled equation can be true? Equal to? If this whole term is equal to 0 or pi or 1 pi, 2 pi, 3 pi, 4 pi, 5 pi, 6 pi, 7 pi, 8 pi, all kinds of pies, blueberry pie, banana pie, lemon meringue, apple with vanilla, ice cream from Marie Callender's, so good, pie. That was probably a little bit too much pie, right? Okay, now I'm feeling a little sick. Okay, but really n times pi. Okay, n times pi. And oh my gosh, here we are. You know, you just applied all your math knowledge that you ever gained at this beautiful institution to this amazing physical phenomenon, okay, of buckling. Wow, right? That's great, okay? And what this says here is that now if I solve for P from here, solve for P, right here, I get that P is equal to, oh, goodness, I get, gosh, I don't know, what does that look like? Does it look like something funky? Like pi, let's see, pi over L squared, N squared, pi squared over L squared times EI. Does that look okay? Yeah? Yeah? So here, this is pi squared EI over L squared N squared right here. Wow. Okay, so here's this. I bubbled it. I probably bubbled this prematurely. Let me unbubble that. Okay, because this one is not that important. Okay, that one right here. But what this says is, if I apply this load P, okay, if I apply this load P, I'm going to get the buckled shape. Okay, and the lowest number, what's the lowest value that this can be when n equals, well, 0, but not 0. Let's say, what is the lowest non-zero number n can be? 1, right? The lowest non-zero that this could is 1 right here, right here. And when n equals 1, let me do, this is important, n equals 1, we have our critical load. This is the lowest load it takes to buckle the column. PCR pi squared EI over L squared. Critical load. Okay? And the guy who did this was a guy named Euler. Right? So, much respect to Euler. Shout out. All right? Thank you, Euler, for coming up with this equation right here. That's it. Okay? I'm never going to ask you to derive this. Okay? I just wanted you to see that your differential equations mattered. Okay? I know that you probably went through ODE and you thought, what the, right? WTL for what the love, right? But here, right, you went through it and you said, why? And maybe they never told you that you can apply a differential equation for war. Did they ever tell you that? That's what made it interesting for me. My instructor said, man, they use these differential equations to describe the rate at which you enter supplies and extract supplies during war. Like, oh my gosh! Okay, all right. So, okay, I'm going to stop here.